And now let me introduce our presenter. Cary Sneider is the lead writer for the NGSS, as well as a research professor at Portland State University. Cary, we're all yours.
Well, thank you, Ella, and I'm really happy to be here. Untangling Science and Engineering Practices. This is a presentation that I actually developed some time ago, even when working on the NGSS. And I found that it was really difficult for people to get their hands around. Inquiry is something science educators are really familiar with. While there are complaints that not all teachers teach with an inquiry approach, the idea of inquiry among people who have some experience in science and education is really well known now. Engineering is the new kid on the block. And as I'll show in a few minutes, a lot of people think they got it, but they really don't, at least not as expressed in the NGSS. So that's what this presentation is all about. So let's start with the first slide, Ella. And there's a little bit of a lag, I understand, in how long it actually takes for the slides to advance. So just bear with us on this. So first of all, scientific inquiry in the next generation science standards is embedded in all disciplines, in all 8 practices, and at all grade levels. Now, the term inquiry actually isn't used very broadly in the NGSS. There's a new term for it called Science and Engineering Practices. The idea is that inquiry has come to mean a lot of things to a lot of different people. It's written about in so many different ways. These 8 practices now emphasize what inquiry is all about, but they also emphasize what engineering is all about. So that's really what this presentation will be about today, is the difference. So keep in mind that science, inquiry, as expressed in these practices, appear throughout the NGSS. And let's go to the next slide, and you'll see something quite similar. Engineering design is also embedded in all disciplines, all practices, and all grade levels. One of the misconceptions about the NGSS is that you find engineering design only in what is now the 4th discipline. So you see physical science, life science, earths, and then engineering. Engineering design is the 4th discipline because we want students to know about it just as we want them to know about the big ideas in science. So it has become actually another science discipline. But also we want students to be able to do it. And in that sense, it appears in all 4 disciplines. Let's go on a bit in the next slide. And we're going to take a look at how you untangle those. So the big question here is science inquiry or engineering design. How can you tell the difference? So in a case like this, well, you look at these 2 pictures and in your own mind ask yourself, well, which of these is science and which is engineering design? Let's go on to the next slide. So I like to start out with a session that I'm teaching with some diagnostic questions. So I want to get your opinion about this. So in one moment, we're going to look at a poll. And it's asking for you, oh, here's the poll. How can you tell the difference between science and inquiry and engineering design? So what's your current thinking about that? So I'd like you to choose one of these. Select the one that you think is the best answer. So you look at what the students are doing, or should you ask the students what they're doing, or should you ask the teacher what the assignment is, or it's not possible to tell. They're so similar. So let's see. Take your time and vote. So 3/4 of you had voted so far. I would appreciate if all of you vote. I'd love to see 100% there, just so you kind of indicate your current thinking. Let's give it another 10 seconds. Okay, let's show the results. Not everybody's quite willing to place their bet yet, but we have 81% who have voted. And it looks like the majority is to ask the students what they're doing. Only 12% indicated look at what the students are doing. So that first slide where where we saw some students looking at working with some chemicals and someone else looking at a robot wasn't quite enough to just look. So 41%, that's the majority, ask the students what they're doing. Only 12% ask what the assignment is, but 1/3 of you say it's just not possible to tell. They're so similar. So remember what the title is, Untangling Those Two. So let's see if I can persuade some of those 1/3 of you who said it's not possible to tell that it is possible to tell. So next time we see this poll, I want to see if some of those votes might be redistributed. Okay, let's move on. And let's look at the next slide, please. I don't know if you, oh, here we go. Next slide. That's me. There we go. Okay. So first of all, engineering design is not new. Science teachers commonly present engineering design activities such as building tall towers. So it's Friday afternoon. We've done a lot of work this week. We've had a little quiz yesterday. You guys did fine. So we're going to build some towers. That's another thing about science. And here's the task. Here's 20 straws, paper clips, and sponges to build a tower as tall as you can. We'll have a contest and see who can build the tallest one. Well, it seems like science. It's technology. They're engineering a tower. Isn't that engineering? Maybe not. Let's move on. Another activity is building bridges. And another, I mean, I've done this actually. I hate to think how long ago when I was teaching middle school in Costa Rica, we built bridges. Those are the days we had cards for computers. And every team had so many cards and 20 inches of tape, and they designed a bridge, and then we would test them with books and to see how many books it would hold. And it was really neat. The kids had a great time, and they really did some thinking, and they would observe each other's, and they would redesign them. So building bridges, is that engineering? Maybe so, maybe not. Let's take a look at the third one. The third activity that is very commonly done is the egg drop. Water filtration systems. We aren't at the egg drop yet. So this is another common activity, developing a system to take water. And often the kids will take some actual water out of the tap and then throw some stuff into it and have a bunch of materials and then design a system for filtering that water so it's drinkable again. Again, could be engineering, maybe not. Let's move on to the next slide. And okay, so we don't have a slide about the egg drop, but that's another popular one. Here's a raw egg, and here's a bunch of materials, and the job is to put something together to cushion the egg when it's dropped. And so the question is it engineering? So remember, engineering is embedded in all disciplines, in all 8 practices, and all grade levels. Let's look at those practices in particular, because that's where we can really determine if it is science or engineering. So let's go on to the first practice. And by the way, this is Gibson in the background. Gibson, my cat, often helps me out with webinars, keeps me on my toes. Okay, so the first practice is asking questions and defining problems. This is one of the 2 practices which is really quite different. So science begins with a question about a phenomenon, such as why is the sky blue, or what causes cancer. Engineering begins with a problem, a need or a desire that suggests an engineering problem that needs to be solved. So when you think about those different activities that we were just watching, Are the students involved in defining the problem? Or is it just the teacher giving the kids the challenge? So remember, these are the practices that we want the kids to develop these abilities. So if the situation is we're going to build a bridge, what do you think a bridge should be able to do? And the kids say, well, where are we going to build a bridge? And you can say, well, we're going to build it across this river. There is no bridge right now, and we have to go all the way around Elm Street to get to school. What if we're going to build a bridge here? What would it need to do? And the kids start thinking, well, it needs to have be strong enough for a truck. It needs to be have kids walking to school on it, and so forth and so on. The kids are defining the problem, then it becomes engineering, not only if the teacher gives the challenge. So again, science is they're investigating a question. And so when you look at these two kids in this picture here, one of them might be saying, huh, I wonder how this little thing actually makes electricity. That's science. The other one might be saying, I wonder how we can improve this turbine so it generates more electricity. That's engineering. Let's go on to the next slide, please. So developing and using models. And again, science will use models. Scientists use models to model the natural world. They think they understand how something works. Let's develop a diagram of it, or a physical model, to see if that's what's really going on. Now, I can't quite picture what exactly is going on in this picture, but let's suppose it's a Jell-O mold. That might be a model of some substance, and we want to see if different Jell-O molds of different sizes would wobble at different speeds. Engineering would make use of models and simulations to analyze existing systems, to find out where there might be a flaw, or to test. Another reason to build a model is you think you know how to make something work, and you want to test it to see if it works. So imagine making a Jell-O mold because you want to try to see if you can minimum earthquake damage to a building. So you put a Jell-O mold down as kind of a damper, and then you put your building on it, and then you shake the table to see if it actually reduces the amount of shaking that actually is transmitted to the building. So engineers use models to test their solutions to problems, whereas scientists develop models to better understand the system so they can better answer a question. Next slide, please. We're moving on next to investigation, which is the third practice. Now, investigation is kind of the quintessential idea of scientific inquiry. So you have a question, and the question might be, what's the best way to get our seeds to germinate? How much water should we use? So we set up an investigation. We set up 3 different plots, and we plant our seeds, and we water them in different ways. Or we put some of the dark and some of the light. That's an investigation to answer a question. That's science. Engineers might have 3 different designs to see which works best. And they will build 3 models, and they'll test them. Or they might build a single model and test it under different conditions to see when it breaks down, when it no longer solves the problem. So there's always an outcome to an investigation. And the engineer will measure some outcome to determine if it solved the problem. The car, will it go fast enough? Or the change to the ecosystem to see if it attracts butterflies. So those are engineering issues. Science, on the other hand, will carry out an investigation to answer a question. What is the relationship between the amount of water and the amount of plant growth you get? So they'll both do investigations, but for different reasons. So let's move on to the next slide. And the 4th slide, if I remember right, is about analyzing and interpreting data, because whenever you have an investigation, you're going to collect data of some sort. And so to make sense of that data, you have to record it and graph it and then interpret it and figure out what it means. This is one of those areas where if you're doing science or you're doing engineering, it's almost impossible to tell because in both cases you've got typically a controlled experiment where you have an independent variable and a dependent variable. And you've made some measurements and you've made some careful efforts to keep all other variables the same. So both of them will do it. In order to find out if a person is interpreting data for the purpose of science or engineering, it has to say, what are you trying to find out? Or what are you trying to do? And then you can get a pretty good clue. Now these two, it looks like two astronauts testing some odd vehicle, are trying to collect data of some sort. And my guess is there's some scientific question they're asking. And the people who designed that vehicle had to do a lot of investigations to find out how many wheels does this thing really need, and can we do what we're hoping? Will it do what we hope it will do? Will it go as fast as we think it will? So there are two very different types of data and interpretations that will need to be done. Let's go on to the fifth one, which is mathematical and computational thinking. Now, math is important in engineering and in science. So in science, it's usually a way of representing different variables and their relationships. In engineering, it's the same. You want to represent variables and relationships, but there you're often use mathematics in many different ways. So for example, if you want to create a design of something and you want to make a small version of it, you have to scale it. So scaling is a mathematical concept and mathematical ability, ratio and proportion. In science, you might want to use ratio and proportion as well to understand how something functions. For example, rates, speeds, and so forth are all ratios and proportions. So miles per hour, miles per second, for example, and acceleration. So understanding different concepts of motion. Gibson's going to help with this one. Computational thinking is one of his most interesting things to do. We call him computer cat, which is he's trying to do right now. You can't get up there now, Gibson. You have to move on a little bit so I can see the screen. Thank you. So computers also, scientists and mathematicians use computers, but scientists use them to answer questions, and mathematicians and engineers, of course, to solve problems. Let's move on to the next one. And number 6 is, again, where you can really see the distinction. He really likes to sit up there on the screen. I think he wants to be on today. The other major difference in engineering and design is number 6, because constructing explanations is what scientists do. And in a sense, you can say, what is the most important thing a scientist can do? And that's explain some phenomena, maybe using a theory or hypotheses that derive from a theory. But it's really understanding the world and providing those kinds of explanations. Whereas an engineer, the most important thing an engineer will do is how to solve a problem or how to meet a need. Okay, Gibson, you have to move on a little bit. There we go. All right, so if you think about it, practice number 1 and practice number 6 go together beautifully. Defining a problem, solving it. Asking a question, answering it. So 1 and 6 are the practices where there are the greatest differences. The others are quite similar, but again, they're in service of different purposes. Okay, let's go on to number 7. I think I'm repeating myself, and you're tired of it. All right, so engaging an argument from evidence. Again, the scientist wants to engage in argument. Okay, Gibson, you can sit there for a minute. Engaging an argument from evidence is something that scientists need to do after they've explained something. And someone says, well, are you sure that's the case? And the scientist has to say, well, here's my evidence for it. Now, the engineer has a little different task. The engineer thinks he solved the problem or she's solved a problem, and presenting that solution to the client would say, well, here's the 3 different solutions that I came up with. This one works best. Well, why does it work best? I'll show you the evidence from the tests we've run. So in both cases, the scientist and engineer would be arguing from evidence. Let's go on to the 8th one, the final, which is obtaining, evaluating, and communicating information. Now, one of the most interesting things about the framework and the next generation science standards is that it recognizes that scientists and engineers and kids learn a lot from reading. And to read, though, it's important to read critically and to really evaluate the source and to synthesize the information, to really think about that. Scientists and engineers, a number of studies have shown that scientists and engineers spend fully 50% of their time doing that, reading each other's papers or writing papers. So both receiving and sending out information. A lot of people think, well, scientists spend time in their laboratories and engineers spend time in their shops, and that's what they're always doing. Well, no, that's not really the case. They also spend a lot of time in meetings and discussions with each other, because it's that exchange of information in the case of scientists. It's that teamwork in the case of engineers that really allow them to do their work. So this last one about obtaining, evaluating, and communicating information is also very important for both. But again, in this case, they have a different goal. So what it really boils down to is a matter of goal and how to determine whether what you're doing as science or engineering is determined in large part by that goal. But the other important piece of this that I want to emphasize is it's not only the goal that determines whether kids are doing science or engineering. The important thing is, are they doing at least some of these 8 practices? Now, a little while ago I said, well, it's really not engineering if they're not defining the problem. No, not always. That's a little too strong. Because you can start kids off with a challenge. But then you want to involve some of the other practices. So you want to involve them, for example, in when they come up with their solutions, to actually build a model and test it. So that would be investigation and data collection and interpretation, and perhaps mathematical or computational thinking. You want to involve them in evaluating, reading and evaluating information. So the main point is that they don't have to be in every activity involved in all 8 practices in either science or engineering. Because over time, though, you want them to develop all of those capabilities. So at least sometimes you want to have the students be in a situation where they can be asking questions or defining problems. So we're going to move on to the next slide, and I'm going to have to ask Gibson to move so I can see what the next slide is. Okay, so we're at a point again where we're going to take the same poll. Given what you've heard so far, how would you tell the difference between science inquiry or engineering design? So let me ask you to take your poll's about to come up and ask you to take a vote again. These are the same choices, by the way. No tricks here. But I want to see what you think. And vote the way you honestly believe, not necessarily the way you think I want you to think. So we see a very different collection of answers now. And thank you for voting the way you believe, because it's not entirely the way I would vote, but that's good. But we still have just 62% of the people have voted. I really appreciate if all the rest of you do your very best to make a choice. Please place your bets. All right, one more person. If one more person votes, then we can move along. I think we're going to have to stop there. We've got 75% of the people voted. And let's reveal the results so far. Okay, we have a different, I've changed some minds, I see. Rather than 41%, it's up to 67% who would ask the students what they're doing. A few more people would ask the teacher. That's also, I think, quite reasonable. What is the assignment? Still 13% of you think it's just not possible to tell. They're so similar. And I have some sympathy for that because, in fact, as I pointed out, the process is really quite similar. They might be reading something or evaluating or arguing from evidence, and the processes are really similar. But I will add, the way I would vote is I would ask the students what they're doing, or the teacher. But asking the students is even a little more accurate because you find out how the students are thinking about their activity. So if they're really involved in inquiry, then they will say, I'm trying to find out and answer this question. If they're involved in engineering, they're saying, I'm trying to build a bridge that will support such and such and such and such. So my personal opinion is I'm with the 67% here, with a majority who would ask the kids what they're doing. But I certainly have agreed that you could ask the teacher and find out a lot about what the assignment, about which of those two it is. And I have sympathy for the 13% who say, I'm not ready to tell yet. Just can't do it. So let's move on, please. And to the next slide. Next slide, please. Not there yet. Okay. So, as you move on, you can always ask this question. Are we trying to understand how the world works? If yes, it's science. Are we trying to solve a problem? If yes, it's engineering. So I have some examples to show you. And then we're going to have some time after that for Q&A today. So let's move on a bit. See what the next slide is. Okay, so here is another couple of, for second grade, we have these two performance expectations. Now, performance expectations are these statements in the next generation science standards that say what students should know and be able to do. And some of these statements are specifically intended to have students be able to apply their scientific inquiry practices to a particular content or particular core idea. Others are intended to have students apply their ability to solve problems, to do engineering design, applied to the same content or certain core ideas. So let's analyze these two statements. So the first one, plan and conduct an investigation to describe and classify different kinds of materials by their observable properties. Now, I'll interpret this given what I've been saying earlier. So to classify means to determine that these materials are like this, those materials are like that. This is kind of a description of different materials. And it seems to me that there's a question here that's implicit, which is, how are materials different? And so that seems to be more like science. And in a way, many different areas of science begin that way, by trying to understand differences and similarities among the different phenomena being investigated. So if it's trees, for example, well, what's similar about trees? What's different? So getting at the science of botany, you want to distinguish the similarities and differences, and then you learn the differences among genders, among conifers and deciduous trees and so on and so forth. So it seems that the first one involves an investigation to get at a core idea in science. Let's look at the right-hand one now. Analyze data obtained from testing different materials to determine which materials have properties that are best suited for an intended purpose. Now, the core idea is the same, that there are different materials, and the materials have properties. In both cases, the message here is that for second graders, we want second graders to become familiar with materials. So one of the core ideas is about the material world. And at the second grade level, this is what we expect. But the right-hand one is to test them to see which are best for different purposes. So when there's a purpose, you're trying to solve a problem. The purpose might be a material used to pick up a hot drink, or the material might be to cushion the fall of something, then you want it to be soft. Or it might be to pound a nail, make a hammer to pound a nail, so then you want it to be hard. So the idea of being a purpose implies that there's a problem to be solved or a need to be met. So the right-hand one involves the process similar to investigation. In this case, it's to analyze data, so there must be some investigation that provided the data to determine which material is best for solving a particular problem or meeting a particular need. So there's an engineering one, and the other side, there's a science one. Now let's go on to the next slide, and there has some suggestions for thinking about. The whole idea now is to prepare students to accomplish these particular performance expectations. But although a given performance expectation might include a science or engineering practice, instructions could include activities involving either science or engineering. Now this is a case in which you find the core idea is the same. It's materials the materials differ by their properties. But in one case, you approach it through science, and the other through engineering. In other cases, it will just be, there will be a performance expectation about science or a performance expectation involving engineering. As a teacher, you want kids to be able to accomplish either of those. So even though it might be about science, that might be the performance expectation that's guiding the development of a unit, you could have them do engineering activities to get them to that stage, because they need to understand the core idea, and they need to be able to use these practices of both science and engineering. That's, as educators, to understand the core ideas and to be able to apply those core ideas either through science or through engineering. Now, the reason that this whole, that I developed this whole presentation is that both of those need to be done very intentionally. Now, we're used to the idea as science educators to intentionally teach the processes of inquiry, teaching kids to ask good questions, teaching kids to design controlled experiments, teaching kids to read what they're reading with a critical eye, and to make arguments from evidence. Those are really important things that we need to continue to do. But we need to also distinguish when we're doing that from a science point of view than from an engineering point of view. And the processes, the practices, to be more specific, are a little bit different. Not always different, but different in many cases. So I'm going to emphasize the first and the last one. So it's really different to define, to ask a good question that can be answered through investigation, as it is to define a problem. So in defining a problem, for example, and you'll read in the Next Generation Science Standards, you need to come up with a clear statement anyone would understand, simple language, and that also there are criteria for success. So what would a solution look like? What's the function it must have? What are the functions that it could have to be fully successful? And also, what are the constraints? So it has to be using these materials, has to be done in this amount of time. So that's very different from asking a good question in science. Now, looking at the sixth practice, it's also quite different. So being able to explain a phenomenon. You've finished your investigation, you've analyzed your results, and now I can see that the speed of the vehicle depends on the force exerted on it, for example. Actually, the acceleration depends on the force exerted on it. So that's an explanation for motion. Very, very different from the kind of solution that you come up with. Typically in science, there's a right answer. So I just gave a wrong answer a moment ago that speed depends on force, where actually acceleration depends on force. Oh, I got it wrong. Sometimes you do get things wrong in science. In engineering, you don't get things wrong. Some things are more right than other things. So there are better solutions. There is very rarely one solution to a problem. The goal in engineering is to come up with many different solutions, to choose the best ones, the most promising ones, and to test those, and to retest them, and to optimize them, to try to improve the performance. So you get solutions that tend to be better than others. Tell is by comparing them criteria and constraints. It's a very different type of thing than we're used to doing in science. So if we do a good job as science educators and we include these various ideas in our programs, in our curriculum materials, and our activities, that when we teach engineering, kids are going to be talking about the problem definition, the criteria, the constraints, why they're doing an investigation to compare this solution with that solution, or to see what happens under different conditions. We should be able to provide enough information for someone walking in the classroom to listen in, to talk to the kids, to talk to the teachers, to find out if you're doing inquiry or design. And the reason that I'm saying that is because I think it's really important that we be intentional, that we teach kids these skills. Now, I will end this by telling you why I think that's important. Inquiry is important. I mean, I'm a trained science educator. I've done that all my life. My particular passion, for those of you who have been on these before, is astronomy. I am fascinated by what's out there. This idea that we've discovered hundreds of planets absolutely floors me beyond our own solar system. It's just thrilling. Well, I'm motivated by that. Not everybody is. But everybody on the planet, at least this planet that we know of, has problems to solve. Issues come up. And solving problems is something that isn't just what engineers need to do. It's what everybody needs to do. And if we could get kids, or tomorrow's generation when they graduate, our kids tomorrow, to all of a sudden think, I'm going to buy this new device. I have all these choices. Well, how can I make a choice? Oh, I like the brown one. I'll buy the brown one. That's one way to go. Another way to go is say, well, you know, they're all going to cost a certain amount of energy. I really want to limit the amount of energy I use because it's expensive and because it contributes to global warming. Or another problem is there's homelessness in our city. What can we do to solve that problem? Well, criteria. Let's say we can cut homelessness by 50%. How would we do that? So if we can teach problem-solving skills, it is terribly important. Yes, it's great to teach science as well. It's teach and ways of asking questions, and often those two are complementary. You can ask the question, why is there homelessness in our city? That's a scientific question. And it's also it's the science of sociology in this case, but it's a scientific question. And that can help to lead to a solution. So science and engineering work together, and we need to teach both of those. But in the past, we have not taught engineering design to any great extent, and in my view, it's incredibly important that we do that. It's important for our kids and for all of us. So let's see if we have one more slide, at least. Might be a slide about questions. Here's another example, a teaching example. I'm glad we still have time for this one. So when teaching, sometimes it's possible to have the same activity, but to pose a question a little bit differently, pose the activity a little bit differently. So this is an activity about electromagnets. So what you have here is an iron core with a wire wrapped around it, and those two ends are attached to a battery. The battery is not shown in these pictures. So in the first case, the challenge given to the kids is use these materials to determine the factors that affect the strength of an electromagnet. So what are the factors? So the idea is the kids might investigate, and they'd find out that the number of turns of wire is directly related to the number of paper clips it picks up. On the right-hand side, we have the same materials, slightly different phrase. Use these materials to design an electromagnet that will pick up as many paper clips as possible. Now, I've done this with groups of people, and I find out that although both undertake controlled investigations, controlled experiments, the results are very different. Often the one who gets the science assignment to find out the relationships among the variables, period, will do something like, carefully controlling the number of paper clips in a chain, because the length of the chain will tell you how strong the magnet is. The ones that get the engineering assignment to make an electromagnet as strong as possible will use all sorts of different methods. So using both ends of the electromagnet, for example, to pick up more paper clips. So I did this at a teacher workshop once, an NSTA meeting, and I almost decided, and one of the teachers later said to me, Cary, that activity really made the difference. I could see the difference, that sometimes it's a subtle difference. It's not inventing a whole engineering scenario, but it's just a subtle difference in the way you phrase a question, whether or not the kids are answering a science question or solving a problem. But it makes a big difference in how kids go about it. I'm not saying that one is better than the other. We need both. But sometimes when you set it an engineering design challenge, the kids start thinking outside the box in many different ways. How do I solve this problem? And often it is more motivating to the kids to see how to create something that can really solve problems and meet people's needs. Let's go on to the next slide, since I was surprised by this one. Okay, here we are at the resources. So to back up what I was saying, I highly recommend that you read the Appendix F in the Next Generation Science Standards. Now, you'll find it on the website free of charge, or if you buy the version from the National Research Council, they do sell hard copy. The appendices are in a separate volume from the standards. The appendices are like chapters, and they, in my view, go along with the NGSS because they explain a lot. So what I was talking about today is described in greater detail. I excerpted from that to create the PowerPoint today. And then also, what I think makes the best reading is actually a framework for K-12 science education. This is the blueprint for the Next Generation Science Standards. Chapter 3, Science and Engineering Practices, also available from the National Research Council. Again, downloadable free from the National Academy Press in that case. And I highly recommend you read through that chapter and you really get a sense of those what I've tried to communicate in this joint webinar today. So, okay, we have about 10 minutes for questions. So, Ala, do we have any questions so far?
Nope, not so far.
Okay, so we're going to wait a couple of minutes, and I would love to hear from some of you. Comments are welcome as well. maybe the 13% who feel it's not possible to tell because they're so similar, or any of your thoughts really about science and engineering and the differences, or any of the experiences that you have. So I'm going to just hang out here and see if we have some questions. So let me know as soon as you have a question or a comment, Hala.
Will do.
So while I'm waiting, I'm going to make one other comment I'd like to make, actually. I've been working with a couple of colleagues on communicating some of these ideas and encouraging people to do engineering. And the idea that engineering seems to take a lot more time because you present a scenario, kids need time to define the problem and then develop different solutions and test those, and sometimes have an audience of people who are going to decide which are the better ones and which are not, seems to be much more time-consuming than science. But the example that I gave with the electromagnets, I think shows that that's not necessarily the case, keeping in mind that you don't have to do all 8 practices for every activity, that any activity can depend on just 1 or 2 or 3 practices. Sometimes it's just a matter of thinking about an activity that you typically do and say, how can I present this in a way in which the kids would be solving a problem rather than simply asking a question? What would the advantages of that be? Sometimes it's worth trying out just to see how it goes. And sometimes the results can be really pretty surprising. So let me recommend that as one way of dipping your toe in the water if you haven't done this already. Or if you have, analyze your engineering activities that you do and say, how can I enrich them by adding a practice or 2? So, Ala, do we have any comments or questions?
Yes, we do.
Oh, good.
Tom would like to know, do you feel that student-led inquiry has an effect on engagement?
Absolutely. Whenever you have students leading something, it will certainly get other kids to engage. When I was teaching 9th grade, I remember, it was in the days when you could have a general science class, and I had the kids investigating various phenomena. Shadows, I remember, were one of the favorites. And then I would have the kids bring their findings together around the table, and I would have a student be the facilitator. I could sit down the side and be a coach. And what was wonderful about that is when they were listening to each other's presentations, they were much more critical than if I were sitting there in the middle facilitating the conversation. They would look to me then, but when a student was facilitating it, they were much more engaged. Absolutely. I'd also say not only student-led inquiry, but also student-led design can also be more engaging. Whenever you can think of a way to get a student in a situation where he or she is leading the other students, it's much more engaging. Do we have another question?
Yes,
or
we
comment?
do. Yes. Victoria says, I'm a bit concerned about the engineering portion that is to be applied as I have little experience.
I understand that. There's a lot of worry that, oh, I'm not an engineer, I'm not trained in engineering. But we're not talking about, designing a 500-foot tower or a bridge that people are going to actually have to drive across. The idea of solving a problem is pretty straightforward. it's going to take some professional development. There's no question about it. A friend of mine developed the engineering as elementary curriculum, and she tells me she's done a lot of workshops for elementary teachers, and she said that now elementary teachers typically are not extensively trained in science, so for them both science and engineering are kind of new. So with a good curriculum, though, with clear ideas for how to present the material, and with professional development, she said that in a 2-hour session, the teachers typically go away and saying, wow, I can do this. This is really neat. So what makes a difference is having the curriculum and having an experience to work through it yourself. So I don't expect you're going to feel totally comfortable after this presentation. The idea of a webinar is to become familiar with some of the ideas and see what the potential is. I hope I can allay some fears by saying that it's not any more difficult than science. If you're comfortable in teaching a particular area of science, then it's very easy to shift that a bit to engineering, because in this case, engineering, as I'm talking about it, and as intended in the NGSS, is simply problem solving, defining and solving problems. And there are a few things that are new and different, such as the idea of a criteria for success and a constraint, but or making trade-offs where you want more of something or less of something else. But they're not difficult concepts. They just take a little practice to get that level of comfort. Do we have another comment or question?
Yes, we do. Tanya would like to know, she says, as an administrator, it's helpful to have some guiding questions to ask students what they're engaged in and to determine whether the activity reflects science inquiry or engineering design. This would also help with assessing instruction aligned with TKES standards. Have observation evaluation guides been developed for assessment of instruction?
Okay, a lot of questions there. The TEKS, I think you're talking about the Texas standards.
Yes.
Right. And so questions will vary, of course, depending on the particular activity. One of the questions I would always ask is, what are you doing? Tell me what you're doing. So you want to start with an open-ended question if you're talking to a student. And you get typically what the student is trying to do at that particular point in time. I'm trying to measure this. I'm trying to write down such and such. And then you say, well, why? What's that going to lead to? And then they say, well, because we're trying to find out if our solar cooker really works and if it's better than the other guy's solar cooker. And then you begin to develop a picture of what the student is thinking. I always think talking to students is a really valuable opportunity to find out how well a class is working, because for good instruction will show up in students who really know what they're doing. But assessment is formative assessment that a teacher might do, or assessment that an administrator might do, goes well beyond that. From assessing a teacher's instruction, you really want to know how good is a teacher doing at what the teacher is doing? How good is the teacher at instruction? And one of those questions then also is, tell me what your students are. Tell me what your goal is, what you want the students to be learning in this case, and then how are you going about that? So what are the tasks that you're giving them? What are you expecting? And so forth. So there are questions, valuable questions for the teacher, valuable questions for the students. And then there are specifics regarding the particular the particular subject. So I just finished about a 2-year project in physics, where we developed a system for formative evaluation. And And in that, we had to be really clear about what it was, which concepts and abilities we wanted students to be able to do, so that we could ask questions to determine whether or not they could do those. So the types of questions in the Paige Keeley's book, I'm covering students' conceptions and students' ideas in science, is a very valuable sort of thing to get at their specific understanding of specific concepts in science. But it's a big question. It's a really important question, and I can't do justice to it in a brief webinar. I see your time is up. I want to thank you very much for joining us today, and happy to see that everybody stayed with the program. This particular question of untangling science inquiry from engineering design is probably one of the most challenging of the NGSS because it is quite new for science educators. And I wish you the very best of luck with it, and thanks so much for joining us.
Thanks, everybody.